Hello. If we have noticed that everywhere there is transfer of information, say from DNA to RNA and RNA to proteins, it is an information, and that information should be transferred with quite a bit of accuracy. But the problem is mistakes will happen. And if mistakes are going to happen, then should we, is it good? Certainly not. And it's actually expensive for mistakes to happen. In replication, there are mechanisms of how repair can be done by DNA polymerase or the mismatch repair mechanism system or repair system. Similarly, in transcription to RNA polymerase has a way of removing hydrolytic editing, etc. It removes any wrong bases that are added. Similarly, it is also equally important for translation to have proofreading mechanisms. Proofreading is very important because translation is a very expensive process. It needs a lot of amino acid, a lot of ATP to add every amino acid. And imagine a protein of 100 amino acids. It would require many more ATP molecules. And despite spending all this energy, if there were mistakes and the product is faulty, then it is a huge loss of time, energy, space, and everything for the bacterium. This is especially true for bacterium because there is always a race for growing faster and dividing more. And that can happen only if there is quality product made very fast with very little or no mistakes or corrections. It's inevitable that mistakes will happen. All we can do is have corrective measures. Ribosome has proofreading mechanisms, and they're beautiful in many ways. So during translation, ribosome has at least 3 levels of proofreading to see if the correct tRNA has come to the location or not. And this is mostly based on the anticodon codon interaction. This is the codon here, and here we have the anticodon. So if we assume that this is the mRNA, it has the codon here, and this is the anticodon, which is the of the part of the tRNA, and if the interactions between them are present, so there is a part of the 16S rRNA which is about I think it is 2 important nucleotides, that is adenines. I think it's 1492 and 1493 of 16S rRNA. To flip out, they are normally inside in this way, and when the interaction between the codon and anticodon are good, they come out this way. They form hydrogen bonds with the codon and anticodons like this, especially with the first 2 bases of the codon and the second 2 bases of the anticodon. And that interaction, it's stably, the adenines are put out this way, which means if these 2 adenines are now, they were base pairing or interacting with some other molecules inside, but now they are facing outside, which would of course change the way the interactions happen within the 16S rRNA, and there will be a lot of conformational changes. That is a signal for the ribosome to figure out that the interaction between the codon and anticodon is correct, and that is how the proofreading mechanisms happen. Say if these 2 are not flipping out, which would mean that the codon and anticodon are not interacting properly. So anytime that happens, the ribosome is still in the same way, and then the tRNA will be lost from the A site, and there will be a chance for the new tRNA to come, which probably is going to have a better interaction or perfect interaction with the codon. So there are also some of the antibiotics like the paromomycin, which will bind to somewhere in the 16S rRNA here, and because of that interaction, these 2 adenines are put this way out, flipped out constitutively in a way, and because of which Irrespective of whether the codon and anticodon interaction is correct or not, the ribosome is in this state of yes, go ahead, go ahead, go ahead. It's something like the interactions are correct. Actually, these two adenines are not outwards because of the anticodon-codon interaction, but because of the binding of an antibiotic here. The antibiotic, because it binds here, these two adenines will remain in this state forever. And that means this antibiotic is making or forcing the ribosome to go ahead, yes, and it results in the formation of faulty proteins or polypeptides, and that's very expensive for bacteria, and that bacteria might die because of misreading by the ribosome. Yes, there are also other ways of how proofreading can be done. Here is another mechanism in which the factor binding center plays a role. If the interaction between the codon and anticodon are not good, then the EFTU, which is bound to GTP and brings in the tRNA as amino tRNA to the A site, cannot fit with the factor binding site properly. And if it doesn't fit with the factor binding site properly, GTPase activity cannot be initiated, because of which GTP is never going to be hydrolyzed. So for GTP to be hydrolyzed, or for factor binding center to activate this GTP hydrolysis, the interaction between the codon and the anticodon is important. So if it is a wrong one, it will not, GTP is not hydrolyzed. So after a while, this could be diffused out, and a good one or better one, a suitable one, a tRNA could come in, and that will go ahead with the GTP hydrolysis and through the elongation. There is yet another mechanism that we have discussed. It's about accommodation. So assume that GTP hydrolysis also happened, but unfortunately here the codon anticodon interaction is actually wrong, but GTP hydrolysis has happened. Then we have the next step is we have this tRNA that is in this way, and it should, because of the ribosomal movements or ratcheting, we have the accommodation. So that the peptide transfer reaction to occur, the tRNA should be modulated a little bit spatially, and that's called as accommodation. And because we don't have, because the interactions are not proper, if the interactions are not proper, the step of accommodation will be halted. Yes, ribosome has spent energy in the GTP was hydrolyzed, but it is nothing wrong in getting rid of this, because we can only correct and reduce the number of mistake. The cost of retaining this amino acid is higher than losing the whole tRNA here and giving a chance for a new tRNA to be bound here. So what is important to understand is that irrespective, despite all these levels and proofreading mechanisms, there will be mistakes that will happen in the ribosomes, and they are tolerable. They are not actually mutations, so they are not detrimental, or it's not a forever thing. And there is a nice concept of trying to understand what is better and lessons to learn from biological mechanisms. If we want a ribosome to not make any mistake at all, then the rate of translation would be very slow. And if we want the ribosome to go very fast, then the rate of mistakes will be very large. If the rate of mistakes is very high, then the product that is formed, the polypeptides that are formed, are non-functional, and that becomes lethal for the bacterium. But at the same time, if the ribosome should not make any mistakes and it goes very slow, but the others will move ahead faster. And there is only one way to not make any mistake, is not make anything at all. And here is another way that I take from here, is that something is better than nothing. So we have to act, we will make mistakes, We have to ensure that we are having ways to repair the mistakes that we do and so on. I hope you enjoyed the class. Thank you very much. See you later.